Let me first thank Gediminas and his team for bringing us together. It's a great tradition that the Humboldt Foundation is bringing the whole Humboldt family together in various interesting places. In my case, I was a Juzeliūnas fellow. In like 24 years ago, I was hosted by Dan Kleppner, actually, at MIT officially. And still I'm invited 24 years later, and I'm really enjoying being part of the Humboldt family. Today I want to talk about some experimental work that we are doing at the University of Stuttgart. Here you see a picture of the experimental apparatus, but before doing that, just in case you are also interested in other topics, this is what we are generally doing in my institute. We are doing experiments with interacting atoms and molecules. Some of you may know our work on magnetic quantum gases. We are also working on quantum computing and simulation with tweezer arrays. And we are working on vapor cells and thermal gases in various contexts. So if you are interested in these kind of topics, I would be most happy to talk to you about this. And just as an advertisement, this is the website that we have on our quantum computing project. And you know, we are from the south of Germany, where we like the umlaut a lot. And so this is the quantum land with a umlaut. That's how you can remember this. And I'm mentioning this because it, among many things, for example, you can have access to a emulator that emulates the Rydberg platform with up to 30 qubits, and you can program it with a drag and drop tool. It also contains tutorials, and the ones that know me know that I'm always trying to also do a lot of outreach and talk to the general public. And so if you want to teach students about quantum computing, let's say on the high school level, avoiding, for example, the notion of complex numbers, then you should click on this site as well and check it out. Actually, there, this is all in English, so it is useful for all of you, hopefully. Yeah, you are invited to look and hopefully find it useful. But today I want to talk about one activity that is using a novel, let's say, quantum gas microscope that is based on the spatial and temporal detection of ions that we are creating from ultra cold samples. And this microscope allowed us to study a new molecular bond that was advertised already. And it has a very good spatial and temporal resolution. So it allows us also not only to image the structure of this molecule in real space, but also its vibrational dynamics in real time. And so let's see how far we get. The microscope itself is based on ion optics, basically, yeah, that start in a chamber down here, where we prepare a cold sample in an optical dipole trap or in an optical lattice. At some time, T1, we are exciting some of these atoms here to either the Rydberg state or directly ionize it, photoionize it, making an ultra cold ion. Then at some later time, T2, we are switching on the microscope. So that's a very important feature of this device. It is a pulse device, meaning that in this time interval from the excitation to the detection, the volume is going to be essentially field-free, meaning that an ion, for example, can live here for 100 microseconds or longer without being dragged away by some stray fields. Yeah? And then at some moment in time, T2, we can switch on the extraction electrode and image the charge distribution that we have by so-called Einzellenses, yeah, 3 of them, and we magnify this image on to a multi-channel plate. where we can then detect the spatial coordinates and the arrival time, T3. This arrival time tells us either the third dimension, sort of how far away from the extraction electrode the ion was starting, or if we have different species with different masses, of course, we can use it as a mass spectrometer as well. So this microscope has a very good time resolution, actually on the order of tens of nanoseconds. It has a very good spatial resolution, about 200 nanometers or better, which is better than the Abbe limit of optical detection technique. As I said, it is able to do 3D images of a bulk ensemble. You don't need to have a trapping lattice or something to do the imaging. It has a very large depth of field also. Yes, a normal, let's say, fluorescence quantum gas microscope is often restricted to a very thin plane, yeah, because of the Abbe diffraction limit. This one has a depth of field of 100 micrometers or more, because ions have a very small de Broglie wavelength and there's no diffraction limit involved at all. And what is very important is, if you are able to follow the trajectory of an ion under this ion microscope in real space, you are also able to compensate any possible stray field. Very good. For much better than any other technique that we used in the past, like, for example, Rydberg Stark mapping also. Yes. So we are able to control electric stray fields in this area down to the level of 0.1 millivolt per centimeter. Yes. This allows us in turn to prepare a cold ion that we make from a cold cloud and keep it around without any trapping field, yeah, and let it interact with the other neutral atoms that are sitting there as well. Yes. So in contrast to a lot of other groups that are investigating these hybrid systems made from ions and neutral atoms, we don't even need a trap. Yes, we just keep the ion in a field-free space. Good, so this is how it looks like. I just show you a few drawings. It's an experimental physics talk. So you see, this is actually an elaborate mechanical setup. And also the electronics behind it is non-trivial. Yeah, I mean, you can imagine that switching on electrodes from this noise level, yeah, 0.1 millivolt to like 500 volt is not an easy task in 10 nanoseconds. But yeah, this is all I'm going to say about this in this talk. What you see here is that this is a standard Siemens slower, yes, in this case for rubidium atoms, and we are having a small, let's say, tin can here, where we are preparing our cold cloud of rubidium atoms before we do our experiments. Okay, so what can you do now with this? The first example that I'm going to show you is, I mean, we are going to take one of our cold rubidium atoms and put it in with several lasers to the continuum, just above the continuum, to the ionization threshold, such that this ion has essentially the temperature of the initial rubidium atom. Yeah. And then we can produce a rubidium plus inside an ensemble of rubidium atoms, yeah, and we can follow it. For example, the electron disappears. Yes, we have this is a very light particle. It disappears. Yes. So we apply an electric field, and we can drag the ion in a controlled way from the left to the right, for example. Yes. And as they are moving, they are going to collide, yeah, with these rubidium atoms and undergo Langevin collisions. And the way they do that can be followed now in real space and in real time. Here you see an example. So this is the shape of our initial cold cloud. And we are exciting with a focused laser here ions at this initial time. These are the red points here. They are spatially localized, but in the third direction, this is just a laser beam that is producing a line of ions. And then we drag them to the right with 1.5 millivolts per centimeter. And what you can see here is a top view, yes, is that for a very low density sample, some of them actually don't collide at all. They make a ballistic transport to the right, and they end up in this blob here. But some of them do a single Langevin collision, and they are scattered, and that produces a halo basically behind them. And we can measure this halo in 3 dimensions. It's a 3-dimensional picture. Now, with this kind of setup, you can measure the mobility of an ion in a Bose-Einstein condensate, for example. If you change the electric field, you can measure either the increasing kinetic energy or the drift velocity. Yeah, if you do this now in a dense ensemble, there are so many collisions that eventually, after some initial ballistic acceleration, there will be a constant drift velocity. You can say, I mean, this is a measurement of the ohmic resistance of a Bose-Einstein condensate with respect to the transport of a single charge. Okay, that's one example, yeah, what you can do with this kind of microscope. But let's go to this other situation where we now have also Rydberg atoms involved. Yeah. So if we talk about Rydberg atoms, we have to remind ourselves on the behavior of Rydberg atoms in an electric field. And of course, the atom can be polarized. There will be a dipole moment that is induced by an external electric field, meaning that the electron wave function shows a Stark eigenstate that has a charge, a center of mass of the charge on one side of the nucleus, and that produces a large dipole moment. Yes. If you plot the energy levels in the electric field here, then you see 2 kinds of states. One are the high L states that are essentially degenerate, like in hydrogen, and they are showing a linear Stark effect. And then there are the low L states, like this S state here, for example, that show a quadratic Stark effect, because you first have to induce the dipole moment, and then there is the interaction with the electric field. Okay. Now, if I think about the situation around an ion, yes, I showed you we can make an ion. Yeah, let's say this is the ion. Then around this ion, I have an electric field. It falls off like 1/r². Yeah. So I can convert this Stark map into a distance-dependent molecular curve. That's exactly the same plot that I showed you before. I have replaced the electric field axis by a distance axis, yes, using this 1/r² law here, yes. And now you find the same S state again and the hydrogen-like states here, and you see some of these are, of course, high field seekers. They are going to be attracted towards the ion, and others are low field seekers, like this one. Yeah, it will be repelled from the ion. Now let's look at this in a little bit more detail. For example, let's look at this S state. It is a high field seeker, so it will be attracted towards the ion that is sitting somewhere here on the left side. Whoops. Okay. But eventually, you see, it is going to cross actually with these high L states, and there will be a lot of crossings here, and you have to understand the dynamics around these crossings here to see what is actually going on. Now, if you focus for a moment at the long distances here, let's go all the way out to many micrometers, then of course this interaction causes a blockade effect. Yes, just like the famous Rydberg blockade, where one Rydberg atom blocks the excitation of a second one. Here the ion can block the Rydberg excitation at all. Yeah? And of course this blockade is even stronger than the Rydberg interaction, yeah, because there is a charge, yes, that is producing this electric field, and not just a polarizable Rydberg atom. Okay, so you can measure this Rydberg ion blockade or ion Rydberg blockade experimentally. That's some years ago, where we have measured this, where we basically excite this ion and then drag it away a certain distance from the initial excitation volume, and then measure whether we can excite a Rydberg atom or whether we cannot excite it. And then in this trace, you see, for a certain time, while we are pulling the ion out, we cannot excite it, and eventually we can excite it again. This kind of measurement can be turned into a blockade radius measurement. You see this blockade radius in this case at n equals 90 at 90 here is even 20 micrometers, so very, very long distances. Interactions are showing up there. Yeah. And essentially what shows up here is the C4 coefficient of this 1/R4 potential. So this combination of a single ion and the Rydberg atom is interesting. There's blockade physics, but there's even more. Namely, if you now look at this upper part here of this energy, of these molecular potentials, you see this P state gets attracted first. It's a high field seeker, but then it crosses with the low field seeking high L states here, yes? And there's an avoided crossing. And if you zoom into this avoided crossing in here, you actually see a molecular potential curve that in first approximation is a harmonic oscillator. You can quantize it and you can get vibrational states. Now, if you want to do the theory correctly, you have to do something more, and that was done in these two papers here. That's the Reitel group, and that's the group of Johannes Hecker-Denschlag. Namely, if you look at this ground state here, it is a very small wave packet. Actually much smaller than the size of the Rydberg atom. Meaning that you have to treat the charge distribution in this Rydberg atom in a multipole expansion. It's not enough to just look at the dipole moment itself. Yes? So you do a multipole expansion up to the 6th order, which corresponds actually to the length scale of this wave packet. Then you get a quantitatively correct molecular curve like this. You quantize it and you get the correct prediction for the vibrational spacing. And the vibrational spacing is on the order of 10 megahertz, which is great because that's the energy resolution that we typically have in all of these experiments. So we can try to attempt to measure these vibrational states. Just to remind you, what is the binding mechanism in this molecular state? I told you it starts with a high field seeker and goes over into a low field seeker and back. So it oscillates between high and low field seeking states. And in terms of the dipole moment, it just means that the dipole moment is constantly flipping the sign. Yes. And this is what is shown here actually to scale in this little movie. Yes. Here on the right side, you see the Rydberg orbital. Sometimes it has a dipole moment to the right now. Then it oscillates and then it has a dipole moment to the left. Yes. And on the left side, you see the ion. And you actually see the amplitude of this oscillation is very, very small. Yes. On the scale of the binding energy, which is 4 micrometers here. So this new molecule, this molecular ion, I should say, because it's a charged molecule, the binding mechanism relies on this flipping dipole moment. You can do the vibrational spectroscopy, or you can resolve the vibrational states very nicely. Here you see the vibrational ground state and a few of the excited states. If you compare it to the prediction, that's the gray lines, it actually perfectly fits. Yes. So we understand these molecular potentials on that level very well. Now, this is not yet using the microscope, right? It is just doing conventional spectroscopy. So what can the microscope do here? Well, let's now look at the shape of the molecule, yeah? Because we can detect the ion and we can detect the Rydberg atom. And the way we differentiate this is we first apply a little bit of an electric field. We rip apart the molecular ion, accelerate the ion. The Rydberg is still neutral, it doesn't follow. And then only later we field ionize the Rydberg atom such that we can differentiate by the arrival time between the ion part and the Rydberg part. And if we do this, we get a spatial probability distribution around the ion that looks like this, okay? That it was actually surprising when we saw this because it has an alignment, yes? The mechanism that I explained to you should be isotropic, right? The molecular potential had no angular distribution, but in the experiment under the microscope, we found this alignment here, yes? We quickly understood that it has to do with the way we excite it, yes, because we are using polarizations in our excitation beams. And if we change these polarizations and this pattern, the angular pattern actually changes. So we understand this pretty well. Here's the theory, and these are the experimental pictures of the molecules. And of course, we can measure the binding length to be 4 micrometers. What's more, so this is actually not challenging our microscope. Yeah, the binding length is 4 micrometers, and I told you we have 200 nanometers resolution. So what can we do? I showed you that this oscillation has a small amplitude, yes, on the order of 200 nanometers or something like this, or even smaller. So how can we make this object vibrate? We apply a little bit of an electric field that shifts the molecular position on the left, on the right side of the ion up or down, and a little bit to the right in this case. If we then excite with our laser with a red detuning, we will only excite on the left side of the ion. This one is out of resonance. This way we produce an initial wave packet that sits, that's a spatial picture actually on one side of the ion, here downwards, yes. Whereas if we have zero field, I showed you these images look like this. Yeah, they have as many Rydberg atoms up and down, but here we have not only induced an alignment, but also an orientation, as someone from molecular physics would call this, yes. But I would say, okay, we have the ion and we have prepared a wave packet on one side. And if we now switch off the electric field again, then of course we take this wave packet and it will start to oscillate, yes, in this molecular potential. And here's the dynamics. You see this is the experimental result. This is the raw data. Here you see some simulations. I don't go to the details. It basically tells you we also understand the vibrational frequency that we measure on the order of 3 megahertz, so that we can follow here in real time. And it is enough to do basically a classical simulation in this potential to understand this. And the decay of this oscillation comes from the unharmonicity in the potential, which is not perfectly harmonic. Good, to summarize, I introduced this ion microscope device to you. We can measure these molecular states in real space and also in the time domain. We were able to apply an electric field and induce an alignment and an orientation, basically, and then observe the vibrational oscillation directly. And so what's coming up? Well, of course, with this microscope, you can now study all kinds of dynamical phenomena. For example, if you are interested in how a Rydberg atom actually reacts with this ion, if it is not in this flipping dipole potential, but in any other potential, you can follow it. And this is a real movie that we made in the lab, where you see some Rydberg atoms falling into an ion, and you see some interesting dynamics. We can discuss it if you're interested later, but I want to point out that this device is actually also able to detect what Christoph was, Jachimski was, where is he? Here he is, discussing this morning, yes, namely charged polarons in bosonic or fermionic environment. And there are many other things, of course, that can be done now. So with this, I wanted to thank you for your attention, and this is the team. We like to go to the mountains, as Kajik knows, yes. This was last year, and actually on Monday we are going again to the mountains, and if you are interested, join us. Thank you.
Okay, Tilman, thank you so much for such an enlightening presentation. Kazimierz Juzeliūnas had already his first question during the talk. The next question is yours too. So.
Okay, I understand that in this big molecule there are ground state atoms between the ion and the Rydberg core.
Not at our densities at the moment. This is actually a low density experiment. And if you ask, how probable is it to find a pair at the right distance, we try in one cloud 6,000 times, and we are about successful in 300 of those 6,000 cases. Yeah, so actually for this experiment, we deliberately reduced the density quite dramatically. what is coming up now, of course, and that's the next question you may ask, is if you have now another one, yes? Let's say you want to not only have a dimer, but a trimer.
Yeah.
That is going to be very interesting because then you have an ion and two strongly interacting Rydberg atoms that form a correlated trimer. And this one we can also look and see in real space and measure spatial correlations.
And in particular, if there is more of these ground state atoms between, there should be some screening effect.
I would say if there's a ground state atom, okay, now it depends on which position it is, yes. If it is not at this position where you have the p-wave shape resonance, let's say, because that's always bad in rubidium, then I would say it just shifts the energy level a little bit, yes, not much more.
Thanks.
You mentioned trimers, but maybe there is a possibility to observe even something bigger with more Rydberg atoms, yeah?
Yes, absolutely.
So
it's just a matter of the success probability to make them, but our detector is counting individual events. So actually I showed you this vibrational series. The signal to noise was rather good. I saw that near was, oh, it's okay. And the reason is because we are doing a post-selection on double events. And of course, if we go for trimers or polymers, then we do a post-selection on triple events or many events, which is helping us to basically get rid of all the other background. Yes.
Okay.
You read me wrong. I was actually wondering what's the other vibration level on the left.
Okay. So that was another potential curve that is. Yes. Okay.
Okay.
So what was it?
It's another potential curve that is also showing up because there's a splitting here. This is a p state. Yeah. So the p state has not only a single level here, it has actually two other levels here. Yeah? So there's some spin orbit coupling. Yeah.
Chin has a next question.
Yeah, okay, fascinating talk. Tilman, so when you show this rubidium ion colliding with rubidium, you see this kind of like a halo.
Yes.
In principle, they have very similar mass. I would have thought this halo would cover, will be much larger. There would be just like kind of BEC collision. They have a halo that cover this.
It's basically a spherical halo that you get around this.
Right,
and
but it looks like but we had thought that the halo should be larger. That will cover both the initial position 0 and 80. Right, at the moment it looks like this halo only.
No, you are dragging it to the right side. So the center of mass after the collision is here, and around this position you get a spherical distribution.
I see.
Yes.
Okay.
And it is, I mean, this is a line, so you have to convolute it with this initial line in the third direction. That's why it's not a perfect sphere. Yes, it's a sphere that is sort of dragged a little bit because of the initial distribution is a line. Yes.
Okay, and related question, can you determine the kind of scattering length from this
This
process?
is still a classical Langevin collision here, yes, because in rubidium, as Christoph was explaining, the S-wave limit is actually below 100 nanokelvin, and we are not that cold here, yes. So it is still fully classical Langevin collision here.
Got it.
And that is isotropic, yeah, it
Right.
just has no preferred direction.
Critical velocity.
If we would be slow enough, if we would be at this threshold between classical and quantum, then we should see all of these features. And that's actually the upgrade of the experiment. We will switch this to lithium, because in lithium, this threshold is at 9 microkelvin. It actually goes like the square of the mass, yes? So with lithium, you have a much better chance to observe some quantum effects like this. And then in this kind of measurement, as a function of velocity, you can see all the partial waves popping up one by one. Yeah.
Perhaps we can use microwaves to induce molecular dynamics, or like
that's also a very good question, yeah, because if you look at this potential here, here for example, you see this is 20 gigahertz or something like this. So if you shine in microwaves, you can induce transitions between Rydberg levels, of course. And we think this is already present in our experiment. Nobody asked me about the lifetime of these molecules, but this lifetime is actually shorter than the Rydberg lifetime itself. And we think it has to do with spurious microwave fields, uncontrolled microwave fields that we happen to have in our lab, yeah, driving transitions from the bound state to something that is no longer bound, and we are losing the binding. So the lifetime is about 6 to 7 microseconds only, yes.
And measured length of the bond is similar to theoretical one?
Yes, so we get 4 micrometers.
4 micrometers, yes. Okay. Do we have additional questions? Yeah. Let's,
Maybe a very naive one related to the lifetimes. I was
final
thinking,
one.
Is there any chance of Landau-Zener tunneling while shifting?
Yes, you can calculate it for this kind of situation, but that's safe, yes? That's not the reason for the finite lifetime, yes.
Okay, I think let's thank for our speaker.